Good morning or afternoon, everybody, or maybe good evening to some of you. We are starting the next chapter. So, this is going to be average rate of change. It's totally related to chapter 3, even though we're doing chapter 2 homework with this. Hopefully, the first chapter we've done with you, the limits, and after taking a test, it's a learning experience, kind of learning calculus, learning what it's about. Hopefully, you're starting to see how to study for calculus, how much you have to study, how much you have to understand, and some of the details. So it's a learning curve. I know some of you struggled a little bit with that first test. Some of you did fine. It's going to get more difficult. So that's not to discourage you. It's just for you to learn how well you have to know concepts and things in calculus. And you have to practice. It just takes time. It takes time and experience. So I just highly encourage you need to spend the time. When I go through this video, it's not just to get your credit, but you want to understand what's happening. So average rate of change, what does that mean? So rate of change, it's how fast something's changing. You're comparing two things. And so usually when we have average rate of change, it's going to be the change in, could be y or could be something else, over change in x. I'm going to change the size of this. Now, change, we use delta to indicate change. So it's change in y over change in x. So that's rate of change, and it's average rate of change. You'll figure out why it's average. So that's what's happening with rate of change. And you'll notice this formula here, that's just like the slope formula. You know, when you're finding slopes, it's change in y over change in x. But now it doesn't have to be y's, and it doesn't have to be x's. And so that's the concept of average rate of change. And we're going to do an example where it's not going to be y and x. So we're going to do velocity. So let me give you a little talk about velocity. Actually, let me do average velocity. So average velocity itself is a rate of change. So if I say average velocity, what is that? So average velocity is actually the change in position. So you want to know how much your position changed from when you started to when you ended. So you want to know how much your position changed compared to change of time. And we could write that as delta. Sometimes position's S, sometimes we'll use X. It just all depends. So if S represents the position, it's delta S over delta T. So that would be average velocity, which is the average rate of change of the position. So it doesn't have to be Y's and X's when you graph. It could be a position and it could be time. So that's kind of what's going on with average velocity. So I'm going to take a trip. Where am I going? Up here, you'll see this place called Mammoth Lakes. It's my favorite vacation spot. Beautiful hiking, beautiful fishing. There's golf. There's all kinds of stuff up there and good food. And so I like going there. I go there pretty much every summer. But we have to drive there. So I'm going to describe my drive to Mammoth Lakes. And I will get, let's see, which color? This is a nice color. Where are we starting? So if you look, there's Anaheim down here at the bottom of the map, if you're not looking. Huntington Beach. And so where's Garden Grove? Garden Grove is right around here, in between Anaheim and Long Beach, kind of. So that's where I'm going to start my car. And I will be, I'm trying to look at the map, right around here. So you'll see what I'm going to do. I'm going to drive down the freeway. So I'm going to go up Euclid Street, hit the 5 freeway, and now I'm going up the 5. Now that shouldn't be line. And I'm going to go up the 5 freeway, if you look, and I'm going to stop somewhere. Oh, I went too far. Let me back up that line. So up the 5, down the 5, and then right here, Santa Clarita, that area, there's a freeway to the right, the 14 freeway. I want to hit that. So I'm going to exit the 5, and now I'm on the 14. Whee! Palmdale, Lancaster. When I get right to there, I am now in Mojave. If you get to Mojave, it's usually windy, and the desert there is littered with windmills producing electricity. The beautiful scenery is now just, you might think the windmills are beautiful, but I don't. Now you just see windmills everywhere, and the once beautiful just desert landscape is now full of solar panels and all kinds of stuff. So that's how you know you're in Mojave. It might be, sometimes I get gas there, but I'm not going to stop. I'm just going to keep going down the 14. There's Highway, there's a reservoir there, Cartago, and Independence. I'm going to keep going. Actually, I'm going to stop. I should have stopped at Lone Pine. So there's a town somewhere over here, Lone Pine, and I'm going to get gas. I'm going to stop for gas because my tank's getting low, and I want to get food. So I'm going to stop and eat there. Then after that, I'm going to continue on, past Bishop, go on. I got distracted. I went too far. Whoa, I hate when it does that. I went too far. I have to turn around now. I'm going to turn around, go backwards, now hit the off-ramp, get to Mammoth Lakes, and I'm good. So that's my trip. Why am I doing all this? There is a method to my madness. So here's my question. My position changed 360 miles, and it took me 6 hours. So if you compare my start position to my end position, it changed 360 miles in 6 hours. I actually traveled more than that because I went past Mammoth and came back. So the change was 360, not the total distance. So my question is, what was my average velocity? See if you can figure that out. Go ahead and pause the video. I'm going to keep going because I don't have to pause because you're pausing. So average velocity should have been change in position over change in time, which we said 360 miles in 6 hours. So if you divide that, 60 miles per hour. So my average velocity was 60 miles per hour. What does that mean? We'll talk about that. Here's my first question before that. Did I travel at that velocity for the whole trip? So any time during the trip, was I always going 60 miles per hour? Clearly I wasn't, because when you start the trip, you're in a driveway, you're not moving, you're going 0. And then you're going to go faster. When you're in freeways, you're going to go faster. And when you see the police car, you're going to slow down and all that stuff, right? So you didn't go 60 miles per hour for the whole trip. So what does average velocity tell me, tell you, tell anybody? So think about that. Try to explain that. And then I'm going to go to this graph. Here's a graph of my position at different times. So what does this represent? This time is 0. I haven't left yet. And my position, my house, is 0 miles away from my house. I'm going to end 360 miles away from my house. How did this happen? So what's happening if you look at the curve, look at this part of the curve from here to here. Do you see that? That portion, something's happening. And I want you to see, what does that mean for me? Okay, let's count 3 bars over. 3 bars over, my position changed this much. That's my change in position, and that's my change in time, right? Now, if you look at the next 3 bars, I'm going to go over 1, 2, 3, and here, look, my delta S is a lot bigger. That means in the second 3, my distance changed more, my position changed more. That means I must have been traveling faster, right? Hopefully you see that. So in this region, my velocity is increasing because I'm traveling a greater distance. So in that time, I only increased a little bit, that much. But in the same amount of time, now I increased that much. So clearly, if I'm traveling farther in a shorter time, my speed is, or velocity is increasing. Now in this next region, the opposite happens. And you can kind of process this and think about this. Look at that portion. So in this short amount of time, look, my position changed a lot. Bam, right? But if you look in this, my position changed only a little bit. So that means my position is changing slower here than it did from here. It changed a lot there. Look at that. That's a big change, small change. So that means in that region, my velocity is decreasing. Hopefully, you can see that, process through that, think about that. In this next region, what's going on? Well, if you look at the first 2, look, that's my change in position there. If I look between these 2, that's my change in position. Now, if you pick any 2 or any 3, you will see it's the same everywhere. Whoops, I went over too far. Doot, 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 doot. So in that blue region, my change in position is the same for each change in time. So there, my velocity is constant. So process through that and make sure you understand why. And then I'm going to give you one more region, this dark, no, it's too close to the other one. I'll do this funky brownish color right there. In that region, look what's happening. My position is staying the same. I'm not moving. My position's not changing. So in this little region, my velocity is 0. I'm stopped. What does that correspond to in my graph? That's when I got to Lone Pine and I got gas and I ate. So I wasn't moving. I was just sitting there. So that's my velocity, 0. And the rest of the trip, let's talk about this. So my velocity increases. Now I'm going constant velocity. Oh, that's where I realized, hey, I went too far. I got to turn around. So now I'm going backwards. My position's getting less and less. I'm getting closer to home. Here, I stopped again. I probably got confused. I looked at the map or something. And then here, I drove backwards. And I stop here in Mammoth at 360 miles away. So that's kind of how to read this chart. You need to kind of sit there and think about that and make it click. I know the first time you see this, it's kind of blows your mind a bit. So the average velocity, let me show you where that is in respect to this thing. What color? Have I not used a good color? Yeah, the gold. That's golden. So if you look at that line, it has a rise and a run. So if you look at that, that's my change in position. Which I can write as delta S. And if you look at this bottom line, that's change in time. And that's delta T. If you look at this line and you want the slope, you learned a long time ago, it's rise over run, right? Slope. But what's the rise and run of this? The rise and run would be delta S over delta T. Does that look familiar? Delta S over delta T? It should, because that was my average velocity, or my change position or change of time, delta S over delta T. So here's some connections that should be clicking in your brain. This line here is called a secant line. It just connects 2 points on a graph. So this is technically the slope of the secant line. And the slope of the secant line is the average rate of change or average velocity. Wow. 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 So here is the big connection. You need to kind of see this. The slope of the secant line is the average rate of change. That's huge. You need to make that connection. That's going to be like through the rest of the year, that concept. The slope of that line is the average rate of change. So what does the average rate of change tell you? It just tells you over a long period of time, in this case 6 hours, that my average rate of change or my average velocity was 60 miles per hour on this trip. It doesn't mean I was going 60 miles per hour on the whole trip. Clearly it doesn't mean that because I stopped here, my velocity was 0, and I stopped here, my velocity was 0, and here my velocity was negative, I was going backwards, so I wasn't going 60 miles per hour for the whole trip. But on average, over this long period of time, my average velocity was 60 miles per hour. So my question, if you're in the car and you want to know your velocity at a specific time, at an instant of time, how would you do that? Go ahead and pause and think about that. If you wanted your velocity at a very specific instant, how would you find that in the car? Go ahead and pause. The answer, you look at the speedometer. The speedometer tells you how fast you're going at an instant. That's instantaneous velocity. So instantaneous velocity, average velocity. Average velocity is a velocity over time, where instantaneous is a velocity at a specific time. And how do you find instantaneous velocity from the graph? So I'm going to give you this. If you find the slope of the secant line, that's average rate of change. It's a slope. So instantaneous rate of change is also going to be a slope, but it's going to be different. Instantaneous velocity is going to be the slope of a tangent line. So let's look at this picture here. Let's look at a point. I will do yellow dot. Yeah. Let's look at the slope at that point there. Hopefully you can see that. I'm going to move this tangent line there. Clearly the slope is not right. There's the slope of the tangent line at the yellow dot. Wow, it's steep. That means my change in y, change of x at that point is really high. That means I'm speeding. That means I deserve a ticket. I'm going fast right there, my rate of change. But let's look at a different spot. So let's get rid of, whoa, I didn't want to do that. I want to get rid of that dot. Okay. Let's look at a different point. I'm going to put a yellow dot right there. Do you see that? I'm going to move this line down to that point. There's a tangent line. So it's very similar to my average at that point. So I'm going about 60 miles per hour at that particular point. Now I'm going to put a dot even lower right there. Hopefully you see it by the origin there. See that dot? And I'm going to move my tangent line. I got to flatten it out. See that? I'm going slower at that point. Now I'm going to put a dot in the middle of the graph on the brown line. Now you should be able to see if I want to make a tangent line to that, look, the slope of that's 0 at that point right here. At that dot, the slope is 0. That means I'm not moving. My velocity at that instant is 0. Now we'll do one more to make this connection. So towards the end of my graph, look at the top of the graph. I'm going to draw a yellow dot there. Now I'm going to move this, but look what's happening now. that's a negative slope. The slope of that tangent line is negative, meaning my velocity is negative, and it was because I turned around. I'm going backwards. I'm going back towards Mammoth, so I have a negative velocity. So hopefully you see that. The slope of a tangent line gives you the instantaneous rate of change, and a secant line gives you the average rate of change. And I have it as velocity, but those are rates of change. So, average rate of change. Here is the general formula that you need to know. In general, we put f of b minus f of a over b minus a. That is a formula you have to know. So what does that mean? I'm just going to draw you a graph. And so you can see, that's just this formula here. It's going to be the rise over run, or change in S over change in T. Let me show you on this graph. I'm going to draw a function. And I'm going to label some points here. I'll call this A, call this B. Now if we pick those to be A and B, this is going to be the function at A, assuming this is f of x. And then this point here is going to be f of b. So we already learned that the slope of that secant line is the average rate of change. And we'll do more. We'll look at stuff here. That's going to be the run. That's going to be the rise. But if you look at this, that length is f of b minus f of a. Make sure that makes sense to you. Make sure that's comprehending. Pause if you need to. That needs to make sense. Because this is the building blocks of what we're doing for the whole chapter. The length of this red line is b minus a. So the slope of this secant line, this is the rise, that's the run, rise, run, f of b minus f of a over b minus a, average rate of change. Now, if this function were a different function like velocity, v, that'd be average rate of change of the velocity. If it were any other thing, it doesn't matter. You just put whatever function it is there, and that's the average rate of change of that function. So that's hopefully making sense to you. Now, if you want average velocity, you would put final position. I'll do that. I'll do an example right now. I will. Suppose, here's an example. This is a function of my position. I will go 4t cubed plus t. That's my position at any particular time. And I'm going to start with t is 0 and end with t equals 3. The question is, find the average rate of change of my position, or the position, which is s of t, by the way. Also known as average velocity. So the average rate of change, in this case, is my average velocity. Well, I take my final position. Where did I end up? I ended up there. Where did I start? I started there. Over my change in time. Well, s of 3, 27, 54, 108, minus s of 0, which is 0, over 3. So that, I got to do that in my head. Oh, it's nice. 3, that's 90, 18, 36. And assuming our units were miles and hours, I'll just do that, 36 miles per hour. So that's how you find average rate of change, or in this case, average velocity, final position minus initial position divided by change in time. You're going to have some homework to do also, but there it is. All right. I will talk to you guys later. Bye.